So I know the main mini lecture, I said, you know, you should review the haloform reaction mechanism because it's excellent review. And you should. But you know what? I'm going to go ahead and present it here in a little bit more detail and give you some good opportunity to review and pull things together. And how are we going to do that? By looking at leaving groups. So there's where the review comes in. It's really about the leaving group. So when we think about what we've been learning about the carbonyl functional group, what we know is that, geez, oh Pete, all of these are great electrophiles. So, since each of those carbons is an electrophile, it stands to reason that each of them would be happy to react with a nucleophile. And the nucleophile can be anionic, as shown, or neutral. But what's the difference here? The difference is chapter 17 and 18 versus chapter 20 and 21. And the big difference is this guy right here. That in 17 and 18 we had something attached, a hydrogen or an alkyl group, that is not going to go anywhere. In other words, when we do our reaction, for all of these, we know we get a tetrahedral intermediate. But it's the fate of that tetrahedral intermediate that distinguishes between 1718 and 2021, because we know that that's not going to happen. We are not going to kick out a poor leaving group like H-, because that's highly unstable. That would be a big time energy uphill step. So that's not going to happen. Whereas down here, when we're looking at chapters 20 and 21, if we have, say, an acid chloride and my nucleophile attacks, again I get the tetrahedral intermediate. Looks very similar, but now we have a very favorable up, down, out mechanism where we can lose minus Cl minus. We lose a pretty stable leaving group. So that's a quick mini review of these two groups, and really, when you get right down to it, in chapters 20 and 21, in 20 we're focusing strictly on heteroatoms, kind of like we did up here in 17 and 18. At first we looked at the addition of nitrogen and oxygen, and then ultimately we looked at the addition to make, so that would make acetals and acetals. And we also looked at the addition of Grignards and organolithiums. Well, we're doing the same thing in chapter 20. We're looking at the addition of heteroatoms first, looking at esterification, transesterification, hydrolysis, blah, blah, blah. And then we're going to look at those harder, scarier nucleophiles like H- and the Grignard. So, this is the big mini review for those 4 chapters. So how does the haloform fit in? Well, the haloform fits in with in so many ways. First of all, it fits in with, good grief, chapter 6 chemistry, which is, of course, proton transfer. Proton transfer to make the enolate. And once I have made that enolate, well, you know, it can do all kinds of things. Obviously, under these conditions, it's going to be a reversible reaction because I have the conjugate acid right there ready to protonate it and take it right back to the ketone. So at this point, it is a nucleophile in search of an electrophile. So what electrophiles do we have present? Well, in the haloform reaction, the electrophiles that we have present are the halogens. Now, iodine is the halogen you'd use for the iodoform reaction. If you use bromine, it's going to be a bromoform reaction. But in any case, doesn't matter what the halide is, the mechanism is the same. Your enolate is going to react with the Br2 or the I2 and do something we've already seen, alpha halogenation. So I put my bromine right there on the alpha carbon. So far so good. This is all review. What is different about the haloform reaction is that, once I've put a bromine on there with its electron withdrawing electronegativity, I am making these alpha hydrogens more acidic and more likely to be deprotonated. And given that I have a base present, it's pretty easy for that subsequent deprotonation to take place to make another enolate, this one even more stable, and of course that can react with bromine or iodine again, and then I've got two bromines on that alpha carbon. Well, you know what happens next. It basically happens 3 times. So that's it's the first part of the haloform reaction. By doing a proton transfer and doing alpha halogenation, because you're under basic conditions, you ultimately get to the point where you have substituted all 3 of the hydrogens on that methyl ketone. And it's worth pointing out that for the haloform reaction to work, you must have a methyl ketone. Can't be an ethyl ketone, can't be an isopropyl ketone. You need all 3 of those hydrogens to be replaced. So as I said, that's the first part of the reaction mechanism. So what makes this more than just alpha halogenation? Well, you're under basic conditions. So a logical next step that you should fully predict is that the OH minus there's no more protons to remove, so it's going to have to add to the carbonyl carbon. That makes perfect sense. Now, does that get us anywhere? And, most of the time we've said no. We have said that, hemiacetals are not stable, and this is just not going anywhere. I mean, this is a reversible reaction, right? So this is not stable. This would be energy uphill. So dumb move. Predictable but dumb. But wait. It's all about the leaving groups. And now we actually have a halfway decent leaving group. What? You say what? Well, if I kick this back down, and instead of kicking out my OH in the reversible step, I instead kick out what? I break that carbon-carbon bond. Is this mechanistically feasible? And the answer to that question is, boy oh boy, is it ever, because it's going to be irreversible. I kick out CBr3 minus. Actually, the iodoform reaction is much more feasible. It's going to be Ci3 minus. And what makes it irreversible? The almost instantaneous proton transfer between the carboxylate and the CBr3 anion. When it's iodoform, this is a yellow precipitate that indicates that you have cleaved off that methyl. So, by putting 3 halogens onto that carbon, you have made it into a C- leaving group that's actually reasonably stable. Stable enough to be kicked out, breaking a carbon-carbon bond. Who'da thunk? Absolute insanity. So there you go. That is the haloform reaction mechanism in gory detail, and it reviews proton transfer. It reviews the up, down, out. And it reviews leaving group stability. So a lot of packed into that nice little reaction. So the but why is what we've already talked about. It's a stable leaving group. So if you're wanting to stick around for another few minutes, we'll do this example of how you could actually use the haloform reaction in a synthesis. Typically speaking, we don't want to lose carbons and throw them away in a synthesis. That's not green chemistry. That's not good atom economy. But sometimes it might make sense, particularly when you're looking to synthesize something like this, methyl hexanoate, from something that is a hept. I've got a heptanone. I'm apparently losing a carbon on my carbon chain. That's pretty weird. So you always want to compare, if you have your starting material, you want to compare it to your target, because that might give you an important clue. If I'm losing a carbon, some kind of cleavage reaction is taking place, like ozonolysis, or maybe the iodoform. So let's look at this. When I see this is my target, I see that I have an ester, and the logical disconnection for an ester is right there. So I know I can make my ester by, some leaving group here plus CH3OH. We're just going to sketch this out. It's probably easiest, actually, to just esterify your acid under acidic conditions with methanol. Okay, easy peasy. I know how to make that ester. I still just have 6 carbons here, though. So maybe I will just make this the acid, because I like that. It's straightforward and simple. How do I make this acid? Well, thinking of the fact that I have to lose a carbon at some point makes sense to me that I could do this by the haloform reaction. In other words, that maybe I am going to make this hexanoic acid from a heptanone, the heptanone shown here. Okay, that's easy enough. NaOH, I2, that's the iodoform conditions. That will take me to my hexanoic acid. Cool. So right about now I should be paying attention to what my starting material is, a 4-hydroxy 2-heptanone. So I have the 2-heptanone here. What I'm talking about ultimately starting with is this. And if I'm talking about that as my ultimate starting material, that is making me think aldol, screaming aldol. Alright, so how do I go from here back to an aldol? Well, my aldol should look like this. If I let my aldol dehydrate, I've got that, and I can certainly add H2 and PD. I should be able to selectively reduce my double bond. Okay, and this is aldol. The aldol comes from, looks like the aldol would come from 1, 2, 3, from this aldehyde plus this enolate. I'd have to control it. This is looking pretty good. So this would be, I would use heat to dehydrate that. And so actually we've done our synthesis. We can see where 4-hydroxy-2-heptanone came from, but I'm going to keep going backwards. I want to see if I can make this from acetone, which is right here, and 1-bromobutane. Not real sure why I would need acetaldehyde. Okay, maybe I'm thinking I'd have to make methanol from acetaldehyde some way. That's crazy. Alright, so how do I make my butanal? I got to make my butanal from PCC, right? So I'll do the actual structure. CrO3. There's a chlorine in there. This is a mess. You can probably hardly read it, but that's PCC. That would have come from the alcohol. And I know I can easily get to the alcohol from 1-bromobutane by nucleophilic substitution. So it all hinges on the iodoform, but as you can see, if you work backwards from the target, it becomes a lot more straightforward. Okay, so that's more than you ever wanted to know about the haloform reaction and its potential application in synthesis, but it's a great review. So we'll see you in class.